So this is a proportion that I'm working with, and I want to find the difference in these proportions. And we're going to do this two different ways. We'll apply the central limit theorem, and we'll also see what stat-Q randomization thinks about it. So there's some concern that people admitted to the ICU with an infection die at a higher proportion than those admitted without an infection. A random sample of ICU patients was taken. Variables of interest are whether the patient entered the ICU with an infection or not, and whether the patient lived or died. Summary of the data is given below. So this was a real study that the authors of our text found. I took that data and I randomized it a little bit so we get a slightly different version each time, and they're all pretty similar. So it's kind of like the way stat-Q does that randomization distribution. Here I'm just doing it one at a time instead of thousands at once. So this is my new set of data, and I was keeping track of 199 patients in this particular case, and 60 of the infected people. There were 81 that were in ICU with infection, 60 lived, 21 died. Of the people in the ICU without an infection, there were 100 who lived, 18 who died, out of a total of 118. So we have these summary cells on the side and on the bottom. We want to test the claim that the proportion of ICU patients with an infection who died is higher than the proportion of ICU patients without, misspelling Gary, who died. I'll fix that later. All right, so first thing I'm going to do is I'm just going to try to summarize in hypotheses before I start pushing buttons here. So it's a really good idea to take notes on these problems. And I know most of you do. Good reminder. Some days I try to look at something and just do it all in my head. And the problem is I can't reflect back on what I was thinking a few minutes ago very easily. So let's see. We have mu for the infected. And so, no, I lied. This is a proportion. Proportion of infected people who died. So this is proportion. And one reason I write out my variables like this is because if I need to state a conclusion later, I can't state a proper conclusion unless I have good definitions. So think about that. Oh yeah, Harley just mentioned that. Oh, and Tammy, yeah, my doctor said go get some eye drops. So I got something called relief tears, maybe he said to try, and he gave me a few different kinds that I should check out. So yeah, I started using those yesterday, and I'm going to need them after class today. All right, so that was a side chat. Sorry, y'all on the YouTube. Let's see, proportion of ICU patients with an infection who died. And this is one of those conditional probabilities that we talked about. Knowing they have an infection, what's the probability they died? Which is a review we'll look at later. And then there are people without an infection, I'll call that PN. stat-Q would call these P1 and P2. So similarly, this would be the proportion of ICU patients without an infection who died. Now these, because I'm using just a P, this is the population, the whole, all ICU patients in the United States, maybe, could be my population here. And my hypotheses, the null hypotheses for difference in proportions is always that there's no difference. Oops, colon, and so then I would say PI equals PN. The alternative to that, not alternative hypothesis, alternative way to write it, would be PI minus PN equals 0. No difference, they're the same. Alternative hypothesis here is that people with an infection die at a higher rate, was whatever that's asked to test. So that would be PI is greater than PN, or alternatively, PI or P1 is minus PN, or P2 is greater than 0. And the spreadsheet needs these zeros here, so that's one reason I write it in the alternative notation. And then alpha, I think an alpha was given, but I don't recall. Let's go look. here I was given an alpha of 0.5%. Okay, so I guess I have that ready. Now I just need to look at the sample data and draw this out. So start my drawing down here and figure out where the sample data lives. We'll do this on the spreadsheet first and the randomization second. So I'm saying first there's no difference from this value in the null. And then I have to figure out where my sample data lies, and I don't know yet. So as far as the sample goes, I need to know what p hat of the infected is, and I need to subtract from that p hat of the not infected. So this would be my sample statistic here. And so I'm gonna have to go calculate that. I can use a spreadsheet to help me. Once I know the sample statistic, then I can go and find the standard error and the t-score, and then the p-value, kind of in that order. So once I have that, I'm going to find the standard error and then the t-value. And then based on that, I can get my p-value. Oops. Order of operations that has to happen before we can make a decision. So I'm going to scoot this window over for a minute so I can copy some of this data into my spreadsheet. All right, so what are we doing here? We are doing, I'm going to zoom out a sec so I can pick the right tab. Two proportions hypothesis test. Okay, so where is that? Two means two proportion hypothesis test. There it is over there. So this was, I don't remember which example this was from way back last week. Some days last week seems like such a long time ago. Oh, this was the infection one with a different set of numbers. All right, so here I was calculating the p hats based on the x1 and the n1, which was given in my table. So from my table, the infection row said that 21 died out of 81. So that gives me about 26% of them died right there. And then the P2 is my no infection people, and 18 out of 118 died. So the yellow parts are the parts I need to alter. So let's see up here. 0, that's correct. Equals, that's correct. 0 greater than, that's correct. And the alternatives are still correct. Okay. The alternative ways of writing. Alpha, that I gotta change. 0.005 in this case. All right. And we scroll on down, and then the computer calculates the rest for me. It says, all right, your difference in proportions is this. There's a thing I talked about last week called the pooled proportion, which is different than the sample statistic proportion. And that is needed to find the correct standard error. So down here, I have the standard error formula, which relies on the pooled statistic, assuming there is no difference in the sample sizes. So I just do that for you. You don't have to worry about that crazy formula. If you did want that crazy formula, it's in the book, it's in our notes. So here's the cheat sheet I provided last week for the difference in two proportions. And so here, let's get my pointer. Here is that how to calculate the pooled statistic. And then down here is how the standard error was calculated. But the spreadsheet just does it, so no big whoop. And if you wanted to make your own spreadsheet, then you would need these formulas up here to do so. Back here, let's turn it off. Oh, all right, there we go. All right, so let's see. So then from there, when we do proportions, we call it a z-score instead of a t-score. And so here I'm getting a z-score of 0.186. And once I have the z-score, I can accurately draw my picture. So going back to the picture here, in a normal type distribution, the tail, the skinny part of the tail out there, is usually around 1 to 3 standard deviations out there. And my test statistic had a z-score of about 1.8-ish, 1.8, 1.9. So my test statistic is about right here. And that's related to the sample statistic, which was a difference of about, was it 10%-ish, 0.10 something. So here's my sample statistic, 0.107. So almost 11% difference in the proportion of people who died with an infection minus non-infection. So that is approximately sample statistic. My t-value was about 1.86-ish, and I didn't get my p-value yet, but the p-value will be this region out here. So this is my 1.86-ish right there, t, p-value. All right, so let's see, am I doing a right tail here? And sometimes it's a good idea to make a note to yourself so you get that right later. Right tail, please. And that should be this formula right here. So I'm getting about a 3% p-value, 0.03122. That p-value is definitely less than alpha. Oh, no, it's not. Oh my gosh, it's greater. Wow, I already can't read. That is greater. 3% is greater than 0.5%. That's my alpha right there. So what am I going to do? That's a big p-value compared to what I was hoping. I guess I have to fail to reject this. Fail to reject the null hypothesis. With that small a significance level, then what we're saying is these differences aren't different enough. They're close enough to 0 to say, it seems like there's no difference. Is there a difference? Yes. Is that difference significant? No, it is not significant. So in warming up for my conclusion, I'm just going to say this difference in proportions is not significant. What I'm talking about here is statistical significance. So the difference in proportions is not significant, meaning these two proportions are relatively close. And relatively close, that is measured by our alpha here. According to that alpha, they're close enough to be almost the same. All right, so now I'm going to try my conclusion. What should my conclusion be? So this is me kind of warming up for my conclusion. So the data supports the null hypothesis according to that significance level more so than it supports the alternative hypothesis. And the null hypothesis is that there is no difference. And so we have two choices to write the conclusion. We can write that the conclusion supports the null, and we state what the null means in words, or we can say we don't have sufficient evidence to support the alternative, which is usually what someone's curious about. I think I'm going to take that route by talking about what the alternative means. So we do not have sufficient evidence or strong evidence. Conclude that patients, now I'm just going to state what I think the alternative hypothesis means in words in this situation. So don't have sufficient evidence to conclude that patients in the ICU with an infection die at a higher rate than those without an infection. That would be my conclusion here. Notice I don't mention the word hypothesis, I don't mention the word null or alternative, I'm just trying to state, okay, based on what I think my variables meant in the beginning here, what's the implication of my failed to reject? And so this, I believe, is the implication. All right, so next we're just going to double check this in the stack queue randomization to see if we get a similar result. And the result should be pretty similar. We have pretty good sample sizes here, so the central limit theorem is definitely applicable. Let's give it a try. So to use stat key, a couple of things have to happen. I got to get to the right page in stat key. So let's see, from the stat key homepage here, I want a hypothesis test, and then I have a difference in proportions. Okay, so that's the spot I want. This data isn't here, it was given, so I got to edit the data table. And I'm going to do that by taking this data that was given to me here and typing it in. So I'm going to do a split screen here to make this happen. All right, so count 1. So the first group is the infected group, and 21 out of 81 died. So count 1 is 21, sample size 1 is 81. The second group was the non-infection, so the count there of people who died was 18, and the total who, that had no infection was 118. Okay. All right, so I'm done with this for now. This up more. Oh, back here. All right, and then double check, that's that same sample statistic I got in my spreadsheet, about 0.107. And these are my individual proportions, about 26% in this sample of people with an infection died in ICU, and only about 15% of people that had an infection died. And then the question is, based on these sample sizes, is a difference of 10% a big difference or not? And based on our significance level in the central limit theorem, we decided, no, that's not big enough. It's not a big enough difference to count one bigger than the other. All right, data's in here, the null hypothesis stat key sets for us, and then we just generate. That should be enough. Here, stat key says the standard error is about 0.058. My spreadsheet thought the standard error was about 0.057. They're close. And again, randomization won't be exactly the same as the central limit theorem, but it'll be close. All right, and then what am I doing? A right tail test. And then I have to enter, oh, look at there's my p-value, my sample statistics. That key picked it for me. That doesn't usually happen. Usually I have to look over here, grab that number, and type it in. So according to the randomization hypothesis test, oh, look, a slightly different number too. I get about 2.3% of other similar samples will have a difference in proportion higher than my difference. That's the p-value, 0.023. And central limit theorem thought it was 0.03. So about 3% here and about 2.3% there. Are they the same? No. Are they similar? Yeah. If I was using a 5% significance level, they would both yield reject the null. At a 0.5% significance level, both of these say fail to reject. Right? They have the same conclusion. The only place they wouldn't have the same conclusion is at like a 2% significance level, or let's see, something in between. 2.5, if we had a 2.5% significance level, this one would say reject the null, and this one would say fail to reject the null. But that's weird, a weird case. All right, so they agree with each other. I have the same one for each. So that was a hypothesis test for a difference in proportions. Next.